recording the status, so we may proceed. So we're looking at limits at infinity. In other words, we're discussing horizontal asymptotes. All right. Now we're going to, in this section, we're going to discuss what happens when x becomes really, really large. So it can be either large as a positive, in the positive direction or in the negative direction. So we start with this function, this first function that you see there, all right? We want to see what is going to happen to this function when x gets really large, all right? Now, a quick plot of the function, you get something that looks like this. Clearly, you can see that as x gets really large, so as x approaches infinity, so as x gets larger and larger, the curve gets closer and closer to 1, all right? And when x gets smaller, so x goes towards negative infinity, you see that this curve also gets close to 1. That's a very important observation because that is what we call horizontal asymptote. So we say y equals to 1 in this case is a horizontal asymptote. All right, so by definition, this is what it typically looks like. I'm sure most of you are asking yourself, but wait a second, will I be able to sketch this kind of curve in a test? The answer is not necessarily, you don't have to sketch the curve, all right? I'll show you another technique how to find these limits as x approaches infinity or negative infinity of such kind of function. All right, we've already seen this. We say the limit as x tends to infinity of f of x is just equal to L. So we get the output L, which we saw before that y equals to L was a horizontal asymptote. That happens when x gets really large, all right? And take note, x tends to infinity, we're looking at some interval from a to infinity, all right? Now, let's look at this is another notation. You're more than welcome to use this notation or this notation. So you need to choose any of these two notations. I know most of you are familiar with that guy there, so it's fine. Just say limit as x tends to infinity and then tell me your answer. Simplify, tell me your answer. If you can write it in this form, you're more than welcome, all right? It's still fine. It simply means f of x approaches L as x approaches infinity, all right? Graphically, when I say x tends to infinity, think about infinity like you go in this direction, all right? You're heading towards a direction. What happens to the curve? Remember, f of x is your function. Looking at the curve of the function, you see that it gets closer and closer to L, all right? So therefore, you're more than welcome to say that the limit is close to L. All right? Now, look at these two graphs carefully. For the first one, as x approaches infinity, again, the curve is approaching L. Look at this one. All right? This is a horizontal asymptote error. You see your curve cuts this line at many points. We call this a decaying curve. It's also a decaying curve. However, you can see that it still approaches y equals to L. Now, you need to be careful. This now changes our definition of horizontal asymptote. Most of you know an asymptote to be a line that your curve cannot cut, right? But today I'm showing you something where that is actually possible, all right? So such curve is going to cut the asymptote at many points. It doesn't change the fact that y equals to L is still an asymptote. Y equals to L is asymptote as long as it meets that criteria, that is the limit as x approaches infinity of my function, I get L, all right? It means y equals to S, it's an asymptote. It doesn't, we don't restrict you to the definition that the curve must not cut the asymptote. So you need to keep that in mind, all right? Again, we've seen this example. So clearly, we can say that this limit is equal to 1 when x approaches minus infinity. Everyone can see that, right? Minus infinity, think of it as you head in this direction, all right? What happens to the curve? You can see that it goes closer and closer to 1. There we go, you still have 1. Now we give you the definition of limit as x approaches negative infinity. Take note the interval is now from negative infinity to a. We say the limit as x approaches minus infinity of f of x is equal to L. All right? And then graphically, see what happens as x heads towards this direction, minus infinity, your curve is getting closer and closer to L. So you see that limit there is L. Looking at this one as well, as x gets closer and heads towards negative infinity, what happens to your curve? You see there it gets closer and closer to L. All right. Now this is the definition that you need to take note of. All right. The line y equals to L is called horizontal asymptote. If either, so one of these needs to be true. You don't need to show me both of them. You just need to show me one, all right? So limit as x approaches infinity of my function is L, or the limit as x approaches minus infinity of my function still gives me L. There you conclude that y equals to L is a horizontal asymptote, all right? If I say find the horizontal asymptote, you can do everything in one step by just doing this one piece only, or you can do this one piece only. As long as you get an answer L, you know that that is a horizontal asymptote. You don't necessarily have to do both of them, all right? One of these conditions needs to be true for you to conclude that y equals to L is a horizontal asymptote. Now let's look at example. They want the limit as x tends to infinity of 1 over x. Obviously, as x gets big and bigger, for example, look at this. When x is 100, we get 0.01. When x is 10,000, look at this, 0.001. So the bigger it gets, the closer it gets to 0. So in conclusion, you can say that this limit there is just equals to 0. Now if we check for minus infinity, if you check for minus infinity, so before I discover minus infinity, this is just what I mentioned already. We can just see that this limit is equal to 0. Now, this also applies to minus infinity, all right? If I take 1 over some infinitely large number, it still gives me 0. It still gets close and close to 0, all right? Because you're going to get negative 0.000 something which is still close to 0. Graphically, another way is to sketch the graph y equals to 1 over x, which everyone knows, just a hyperbola. You have this positive piece here and this piece at the bottom. Notice it, when x approaches infinity, means we look in this direction. The graph, you can see that it's approaching 0, all right? Now, if you look at x approaching minus infinity, again, the graph there is approaching 0. So it makes sense to, you can actually sketch the graph and find both limits. But you see, in both cases, you get 0. All right, that's why it's important for now. Now, we say if r is greater than 0, so take note r there is that power of x, right? If r is greater than 0, it's a rational number. Remember, a rational number is giving us a over b, where b is not equal to 0, right? So some fractions and so on, all right? But take note, b, the bottom cannot be equal to 0. So if r is greater than 0, it's a rational number, then we say the limit as x tends to infinity of 1 over x to the power r equals to 0. Why is that true? Remember, if r is greater than 0 and it's a fraction, so typically you're going to get square root, cube root, and so on. It doesn't matter what root you're using, as long as it's a positive root. As x gets big and bigger, the bottom will still be going very large. You still end up with 0, all right? Now, if r is greater than 0, it's a rational number such that this is true, so x to the power r is defined for all x. All right? Remember, when we take the limit as x approaches negative infinity, we need to be careful. Why we need to be careful? Because if that power r there is, let's say 1 over 2, which means square root of x, 1 over square root of x, x cannot be negative. You see, it's going to be a problem. That's why they add this extra term here that says that x to the power r is defined for all x, all right? So when looking for the limit as x approaches minus infinity, you need to be really careful because it will only work if this bottom piece here, you can actually evaluate the root of that negative value. In most cases, it's going to be the odd root. So you're going to have something like cube root, fifth root, seventh root, and so on. Once you have an even root, here the bottom is not going to work because you can say square root of some negative value, fourth root of some negative value, sixth root of some negative value. It doesn't work. That's why you see this extra parameter there that says x to the power r is defined for all x. All right. Now let's look at this nice example. Evaluate the limit as x approaches infinity of this rational function. Remember our definition of rational function? Have a polynomial of a polynomial, right? Now, this is a procedure that I want you to do it when I ask you this question. You're going to identify the highest power of x in the denominator, all right? Don't look at the top, look at the bottom, the denominator. So my focus is going to be at the bottom. Find the highest power of x, you can say x squared, all right? So this is my highest power of x, this is x squared. I'm going to divide top bottom by x squared, all right? So you find the highest power of x at the denominator, all right? Ignore the numerator, just focus on the denominator. Now if you divide top bottom by x squared, see what happens? There we divided by x squared, the top we divided the bottom by x squared. Now if you divide each of these terms, remember if you have a plus b over c, then you can just write that as a over c plus b over c. I'm sure everyone knows that already. So if you split each of these terms, so you divide 3x squared by x squared, x by x squared, 2 by x squared, you get something that looks like this: 3 minus 1 over x minus 2 over x squared. At the bottom, you get 5 over x plus 1 over. I need to see this working, all right? When I ask you to find limit as x tends to infinity, don't just give me an answer. That would be a very terrible idea. I need to see that you're dividing by the highest power of x. I need to see the step for simplification. And then from here, you're more than welcome to tell me that this whole thing here tends to 0. So this piece here will be 0 because 1 over some large value is 0. This piece here will also tend to 0. 2 is constant while the bottom is going very big. This one will also tend to 0. This piece here will tend to 0. I'm just left with 3 over 5. All right. So that's basically what you see here. So if you split the limit top and bottom, you get 0 for this limit there, 0 for that limit, 0, 0, and you're just left with 3 over 5. Are you done? All right. Take note, y equals to 3 over 5 is a horizontal asymptote. So if I ask you explicitly, I say find the horizontal asymptote, you need to do this process, but your conclusion say that therefore y equals to 3 over 5 is a horizontal asymptote. Take note, in this case, it won't change if I took the limit as x approaches negative infinity, all right? You will still get exactly the same result. So I'm just showing you here that if you take x, if you take the limit as x approaches minus infinity, look at it, it still gives you 3 over 5, all right? Now, this is where things would change a little bit, and these are the kind of questions you need to pay attention, all right? This is called an algebraic function, all right? Now, the procedure more or less stays the same. That says that you identify the highest power of x at the denominator. So I look at this denominator here, which is 3x minus 5. Highest power of x is just x to the power 1, all right? So it means I divide top bottom by x, right? Dividing the bottom by x is easy. It will just be 3 minus 5 over x. But look at the top. If I take this square root there, so if I take this piece here and I divide by x, it's the same as, remember, x can be written as square root of x squared, all right? So we say square root of x squared is equal to x when x is greater than 0. So if you have this whole root here divided by x, you can just say this root is divided by root of x squared, so that you can take the x squared into the root, all right? Some property you need to remember is if I have, let's say, square root of a over square root of b, all right, so this is the formula we're trying to use there. You can simplify this whole thing as square root of a over b, all right? So if you have square root of a over square root of b, you can have one giant root and then you just have a over b. It's the same idea that we use here, all right? If you divide in the root by x, you can change the x to square root x squared, and then you take the x squared in there, so you have one root. And take note, if you take this limit now, if you split it top and bottom, what happens? Notice it, we apply that theory, that concept of continuity. The limit as x approaches infinity of a root, you know that the root function is a continuous function, so you can take the limits in, all right? So that's basically what they did here. But you're welcome to show me this step, but from here, I'm more than happy if you can just tell me the answer, because this is just too obvious, all right? So if you take the limit in and you split it out, notice that this limit here, this piece here, so these two limits here will just be 0, all right? And you just end up with root of 2 at the top, And at the bottom, you just have 3 minus 5 times 0, so you have root 2 over 3. All right. Then now be careful. We saw the rational function, the first example we did. It worked nicely. Even if you're going from, even if you are pushing infinity to negative infinity, you get the same result. It's not true for algebraic function. You need to be careful. For algebraic function, if the limit changes to minus infinity, the match also changes. All right. Why does the match changes? Because when x is less than 0, remember you say that x is approaches minus infinity. So when x is less than 0, square root of x squared, which is just called absolute value of x, is actually minus x. Everyone knows that from the definition of absolute value function. Absolute value of x is equal to minus x if x is negative. That's how it works. So how is this going to change the solution? Let's look at this. Notice it. The key there is this top piece here. Remember, I said you divide top bottom by the highest power of x at the denominator. So let's just look at what happens at the top. So if I take this top piece and I try to divide by x, remember x is just square root of x squared. The trick here is you need to add this negative value here, all right? Why do I add the negative this time? Because I'm trying to find the limit as x approaches negative infinity, all right? I'll mention again, the absolute value of x is actually equal to minus x, is equal to minus x if x is less than 0. So when you divide in by x, you change it to square root x squared. You need to introduce a negative sign because you're looking at x approaching negative infinity. So this is what the top is going to look like. Now if you simplify top and bottom, take note there's this negative sign there. The only thing that will change is that your final answer will be negative. All right. So this is a typical question that you might be asked, which we probably asked sometime in the past. When I ask you find the horizontal asymptote for something like this, you find the limit as x approaches infinity, and then you need to find the limit as x approaches minus infinity because you're going to get two different results. All right. Any question before I continue? All right, if there's no question, now we've seen that y equals to minus root 2 over 3 is also a horizontal asymptote. Now let's discuss what vertical asymptote is. For vertical asymptote, you focus on the denominator, right? So vertical asymptote is when that denominator is 0, all right? So for example, 3x minus 5 is 0, it means x, that happens when x is 5 over 3. This value here is a vertical asymptote, all right? So I'll mention again, when you find in vertical asymptote, you just need to look at the function, equate the denominator to be equal to 0 and solve for x. That x value there is a vertical asymptote. Why is it a vertical asymptote? Because when you take the limit as x approaches that number from the right, for example, you get infinity, all right? You're not going to get some number, you're going to get infinity or minus infinity. That tells you that x equals to 5 over 3 is a vertical asymptote. Now take note, if you take the limit as x approaches 5 over 3 from the left, you get minus infinity. Now how am I getting infinity and minus infinity? So to test this, you just need to choose a value slightly smaller than this. You plug it in, top and bottom, in the place of x, and just test the sign, all right? And the test will typically give you a nicer number so that people don't plug in decimals here. So you don't have to use your calculator. It will be some value of x that you can actually substitute there without getting some funny decimal values, all right? So you find some value close to this number from the left, you plug it in, you focus on the sign, it will give you a negative value. Already we know that the root function is always positive, so this top piece here that you see, so this top piece here will always be positive, but the bottom piece is what is going to be changing sign. When x is smaller than 5 over 3, the bottom piece will be negative. You end up with plus over minus is minus, so you get minus infinity. And graphically, this is just what you get, right? So infinity, you are pushing that, and minus infinity, you're approaching that. And then for vertical asymptote, remember this is your vertical asymptote. So when you approach this number from the right, you see you're heading towards infinity, or you approach it from the left, you're heading towards negative infinity. Practice, do more examples. Okay, I'll give you 5 minutes to try this example, and then someone needs to tell me what they get. Don't look at the next slide and show me my answer that I gave you. Try and do it without looking at the next slide. Tell me what the answers are for these guys here, all right? So I'll give you 5 minutes to try this first one, and then we're going to discuss this one. See if you can get at least this first one right. All right. I can see that most of you are not doing it. Some of you are just waiting for me to do it. I'm just going to show you the memo. um, Now, you need to pay attention because these examples that I choose on the slide, okay, someone got one. Let's see if that is true, and then they're going to tell me how they got one. I'm not sure if this is clear enough. Let's see if we can zoom in. All right. Now, the example I asked you guys to do is this one here. So your answer there is supposed to be 0. All right. How do you do it? I told you you need to rationalize. All right. Once you see root, please, the first thing that comes to your mind is rationalizing. Remember, there's no denominator, so that rule that says divide by the highest power of x that appears in the denominator doesn't apply here, right? So what I'm testing here is just rationalization. So how do I rationalize? Multiply top bottom by the conjugate of this piece here. Notice it, the sign is now plus, all right? And if you multiply, you end up with something like this. Now, as x approaches infinity, you know that this bottom piece there will get really big because it's a root plus x. So you're going to get a very large value. And the top there is just 1. 1 over some infinitely large value is just 0. All right. And then for the second one, you had limit as x tends to 2 from the positive side. So take note the sign there is important of tan inverse of 1 over x minus 2. Now the idea here is I'm testing continuity, all right? So you take the limit into the inverse function, but your first step should be you need to tell me that the tan inverse function is a continuous function. Therefore, you're welcome to take the limit into the function. And once you do that, remember, if you take the limit as x approaches 2 from the positive side of 1 over x minus 2, this simply gives you positive infinity, right? Because you end up with 1 over 2 minus 2, which is 0, and 1 over 0 is just infinity. So it's positive infinity. Tan inverse of positive infinity. Now, look at how we got the result. As x, so your tan inverse graph approaches pi over 2 as x approaches infinity, all right? So we say tan inverse of infinity would just be pi over 2, all right? So as x there gets towards infinity, your tan inverse graph is getting close and close to pi over 2, all right? And then this is an interesting one, which I know most of you without seeing this solution might have struggled. Now, if you see a question like this in a test, please follow these steps. If you substitute 0 directly there, trust me, you will never get to close to the answer because 1 over 0 is infinity e to the power infinity, it might look like it's infinity. Actually, the answer there is 0. All right. So what is the step? You let this power here 1 over x to be equals to t. Therefore, e to the power 1 over x would just be e to the power t. All right. When I say the limit as x approaches 0 from the left of this function, it means that the limit as t approaches minus infinity. All right. So if you look at this relationship here, so we focus on this relationship. When x approaches 0 from the left, so I'm trying to plug 0 there at the bottom, and this left there means it's going to be some negative value that is really close to 0. You see that 1 over 0, there's infinity, but it has to be negative infinity because we are approaching from the left. So your t there is typically approaching minus infinity, all right? And e to the power 1 over x will just becomes e to the power t because we've already seen that from this relationship. And look at this relationship closely. You can either choose to sketch the graph e to the power t, which everyone knows. This is very easy graph to sketch. You know when t is 0, you'll be cutting there at 1, and you have this kind of shape. Actually, I said when t approaches minus infinity, so when you're heading towards that direction, you see your graph is approaching 0. All right. Another way to look at it, e to the power minus infinity is the same as 1 over e to the power infinity, and 1 over e to the power infinity is just 0, because e to the power infinity is just infinity. All right. So please, this example, you need to pay attention, all right? Don't just do direct substitution. Don't try and put 0 there immediately. It's not going to work. You need to follow these steps so that it becomes easy for you to visualize it and see the answer. Now, what about this? Now, it's a rational function because it's a polynomial by a polynomial. However, notice you're not going to get a number. I'm going to explain why. If you divide by the highest power of x at the bottom, remember that rule of dividing by the highest power of x, we say it has to be some algebraic expression or some rational function, all right? So in this case, you can divide by the highest power of x, which is just x, that is x to the power 1. The bottom there, you have 3 over x minus 1. At the top, if you divide by x, you have x plus 1. Now, notice what happens when x approaches infinity. The top there is infinity, right? Because you have infinity plus 1, it just gets infinitely large. At the bottom, you get 3 over x. That will approach 0. We know that already, 3 over x will approach 0. You'll be left with minus 1. So infinity at the top, minus 1 at the bottom. Infinity over minus 1 is just negative infinity, all right? So this whole thing is going to approach minus infinity. And what does minus infinity mean? It simply means the limit does not exist. So when your limit gives you infinity or minus infinity, it simply means that limit does not exist. All right. Any question? Please go and look at this slide. Don't just listen to what I'm saying and you think you understand. Go practice again, and if you get stuck, go back to the video, follow the video, and then if you're stuck, email me for consultation, or you can email the tutor. You guys are not emailing me for consultation. I assume that you understand your work. Anyways, I'm going to see again if you understand limit when we do our quiz next week. All right, let's continue with the lecture slide. All right, so after that example, we had to discuss infinite limits. All right, so infinite limits, let me just zoom out so that the slide is much clearer. So limits at infinity, how does it work? You have 4 possibilities. This is the first one. Limit as x approaches infinity of your function gives you infinity. All right. Limit as x approaches minus infinity gives you infinity. Limit as x approaches infinity gives you minus infinity. And limit as x approaches minus infinity giving you minus infinity, right? So these are limits at infinity. All right, these are a good example. So limit as x approaches infinity of x cubed. Obviously, you know it's going to be infinity. Why? Because x cubed, as x gets really large, x cubed will just, so the output will just get uh, even bigger, all right? So for example, if x is 10, you have 10 cubed, 1000. Look at what happens when x is 100, it's getting bigger. When x is 1000, you're already sitting in the million, all right? So once you approach values like 1 million, if you cube that, obviously it gets infinitely large, so that is just infinity. Now, what happens to limit as x approaches minus infinity of x cubed? Well, if you look at it carefully, you are approaching minus infinity, all right? So for most of these limits that I'm going to ask you, if you can't directly see if it's infinity or minus infinity, it's easy to sketch a graph. Y equals to x cubed is this sketch that you see here. And we've already seen the limit as x approaches infinity, that the graph is heading towards infinity. And then when x approaches minus infinity, the graph is approaching negative infinity, all right? Precise definition. Remember, I said you need to know precise definition. We've already discussed this last week, so this is just a recap. So limit as x approaches infinity, f of x equals to L. Now, the precise definition, this means that for every exodum greater than 0, there is a corresponding number n, so that x is greater than n, then the distance between f of x and L is less than exodum, all right? So the trick here for you to remember is that x has to be greater than that n, all right? And now when the limit is approaching minus infinity, the only thing that changes is that now your x has to be less than n, all right? Not greater than n, it has to be less than n. Please don't forget this, because if you swap them around, when I ask you minus infinity and you do greater than, then you're doing the wrong thing. It's not going to work. And there's one example. The one example is that we need to prove that this limit here is equal to 0. All right. By mention, you must know infinite limits. At least the examples that you see on that we did last week, and this example at the minimum, you need to know those. So how does it work? Given exodum greater than 0, you want to find an n such that, remember this is x approaching infinity, so we need, if x is greater than n, then the distance between your function 1 over x and 0, so it's just 1 over x minus 0, absolute value must be less than exodum. Now, what did I say you must do? As usual, when doing precise definition, you need to simplify this little piece there, simplify this piece there. Absolute value 1 over x minus 0 is just absolute value of 1 over x, all right? We know that if we do the math, we will end up with 1 over x is less than exodum, all right? So this comes from simplifying this relationship here. Why do I get rid of this absolute value sign is fine, because we want x to be strictly greater than n, all right? So we can just say 1 over x is less than exodum. If you really write this a little different, so if you take the reciprocal on both sides, the inequality sign changes. Remember, A is, I'll just write it here so that you can see. If A is less than B, if you take the reciprocal, you get something different, all right? So 1 over A will typically be greater than 1 over B, all right? So whenever I take reciprocal, the inequality sign needs to change. That's what we did here. So 1 over x is less than exodum. This is equivalent to saying that if I take reciprocal, x is greater than 1 over exodum. Why do I need to do this much? I told you need to simplify so that you get some relationship between these two guys. And from there, you can see what the relationship is. Everyone can see that. We can choose our n to be 1 over exodum. That's the key. You do this math so that when you look at this relationship, you can say that, oh, I can choose my n to be 1 over exodum, and it's going to work. So here you choose n to be 1 over exodum, so that if x is greater than n, remember your n is 1 over exodum, then 1 over x minus 0 absolute value will just be 1 over x is going to be less than exodum. All right. And if you don't see how this simplification came about, this piece here, look at if you simplify here. So if I take the reciprocal here, so I take 1 over x. Do you agree that instead of greater than is going to change to this new sign less than, and 1 over x term is going to be x term. All right. So that's how they got this result. And you can just say by the definition of the limit, this PCS equals to 0. So usually the limit at infinity is usually the easy one because it works easy without any problem. Um, I won't ask you any complicated limits or stuff that you haven't done, like the quadratic one with multiple factors. No, I'll try and stay away from that. For the scope of our work, we'll stick to linear functions. So that is when x approaches a, we stick to linear function. And then when x approaches infinity, we'll try and stick to stuff that look like this. I can even ask you 1 over x squared and so on. All right. All right. From the look of things, that is the end of lecture. Any question from your side? All right.